back to the deep dive, where we take your curiosity, a pretty significant stack of complex source material, and transform it into instant, confident understanding. And if you are listening to this right now, chances are you use digital technology in, the last 5 minutes? Whether it was streaming this audio, checking an app, or even just calculating your commute.
Oh, absolutely. I mean, look, software permeates every corner of life. It powers our global economy, education, communication, everything.
Right.
Yet, here's the core paradox we're going to tackle today. Most people use these incredible, really complex applications without any real understanding of what makes them tick.
It's like driving a car every day, right?
Exactly. It's like relying on this massive, highly tuned machine daily, but being completely unable to tell the engine from the fuel tank.
Okay, so let's unpack this, because understanding these underlying digital systems, from the basic lines of code to the massive cloud infrastructure they run on, that isn't just a niche skill for technologists anymore.
No, not at all.
For any professional, I mean, regardless of your field, if you don't grasp the architectural basics, you're really at a strategic disadvantage.
That's the critical insight from our sources. And the stakes they're immense. Whether you're a student preparing for a job that doesn't even exist yet.
Which is most of them.
Right. Or an educator trying to teach future-proof skills, or a business professional making multi-million-dollar decisions about technology. Grasping this stuff is crucial.
So if you don't get the components, the trade-offs.
If you don't understand the inherent trade-offs, like, say, the cost versus the complexity of massive scale, you just can't optimize, you can't troubleshoot, and you definitely can't innovate effectively.
So here's our mission for this deep dive. We've distilled the key nuggets from the sources you provided.
Yeah.
We're going to demystify the essential components of digital architecture. We'll trace the journey of a concept from just an idea all the way to a functional app. We'll explore exactly how modern infrastructure, the cloud, actually works.
And how AI fits into it.
Exactly how artificial intelligence is integrated as a functional component.
Yeah.
And maybe most importantly, what systemic skills you need to carry forward into this digital-first future.
Our goal here is really to provide that comprehensive shortcut. We want to move beyond the jargon, beyond the fear of information overload.
Yeah.
And by the end of this conversation, you'll have the foundational principles you need to look at any app or platform and mentally break down its structure into its functional, interacting parts.
Okay, so let's start right at the genesis, the moment of inspiration. How does an initial concept, maybe just an idea scribbled on a whiteboard, transform into a massive functioning platform used by millions of people globally?
Right.
I like to think of it as a sophisticated construction project. You don't just start nailing boards together. You need planning. You need defined roles.
That comparison to sophisticated construction is spot on. I mean, the journey from idea to software is a highly structured, collaborative process. The industry calls it the software development lifecycle.
Right, the SDLC.
Exactly. And our sources really highlight that this transformation is fundamentally dependent on 4 key roles working together, often under some pretty intense pressure, to bring that final product to market. It's never just one person coding in a basement anymore.
And these roles, they often have different priorities, right? They're in inherent conflict, which I think is where a lot of the friction comes from.
Oh, absolutely. Let's get into them.
Well, let's do it. So the first role is the business aspect. This is the architect of viability, the person justifying the entire effort.
Precisely. The business role is tasked with defining the strategic need and, crucially, the commercial viability. Before anyone writes a single line of code, the business has to answer these almost existential questions.
Like, why are we even doing this?
Exactly. What measurable problem are we solving? Who is the target user? And critically, how will this generate value? Is that revenue? Is it efficiency, social impact? They define the functional requirements and, maybe most importantly, the success criteria.
And they're always focused on speed to market and keeping costs down.
Always. Which, as you said, naturally introduces tension with the other roles.
Okay, so next up is design. This is where the product stops being this abstract goal on a spreadsheet and starts to become something users can actually, touch and feel.
Design is that bridge. It's the bridge between commercial necessity and human usability. And this role, it covers both user experience, or UX.
Making sure it's intuitive.
Right. Ensuring the flow of the application is logical, it's easy to navigate. And it also covers user interface, the UI. That's how it looks, the brand aesthetics, where the buttons go.
A look and feel.
Look and feel. So if the business team focuses on what we are building, the design team is obsessed with how a human will interact with it. They want to translate raw utility into a delightful or at least a usable experience.
And they're the ones advocating for the user.
Fiercely. Which often puts them in direct conflict with the timelines that the business team is trying to impose.
Okay, and then we move into the implementation phase. This is the engine room, right? Development.
Development is the massive engineering effort. This is where the code gets written. They take the strategic requirements from business and the visual blueprints from design, and they're right. They structure, they engineer the code.
And this is more than just typing.
Oh, way more. This involves choosing programming languages, establishing the architectural framework, which we'll get into in a bit, and building the actual connectivity between all the different components. They're the builders who turn that design into a functional reality.
And their priority is what? Clean code.
Their priority is writing elegant, maintainable, and secure code, which almost always takes longer than the business team wants to allocate. You see the tension building.
Yeah, you really do. And finally, the essential, often underestimated, but supremely critical role, testing.
Or quality assurance, QA. This is the risk mitigation step. This team's job is to rigorously, systematically attempt to break the system before the user does.
And this is more than just clicking buttons and seeing if they work.
So much deeper. Our sources really emphasize this. Testing ensures security protocols are unbreachable. Make sure performance is fast, even under heavy load, and that the system scales properly when, say, 1 million users all hit it at the same time.
And this is where the biggest internal conflict usually lies, right? The business team wants to ship the product yesterday to start making money. But the testing team comes back and says, whoa, hold on, we found a major security flaw. We need 2 more weeks of rigor.
Absolutely. That tension between speed, which is business and development, and rigor, which is testing and quality, it's the defining dynamic of the entire software lifecycle.
But a good testing phase must save so much money and reputation down the line.
Astronomical amounts. And these 4 roles, business, design, development, and testing, they don't just do their part once. They have to cycle repeatedly, constantly refining, iterating, long after the initial launch.
Okay, so that's the team. Now let's look at the structure they're actually building. When we talk about digital architecture, almost all modern software, from the simplest little app to the most complex trading platform, is fundamentally split into 3 distinct interacting components.
Right.
I call this the architecture triumvirate, but maybe we should call it the 3 pillars for clarity.
I think the 3 pillars works perfectly for our listener. This is probably the most important foundational concept for demystifying these systems. It's the essential split between what you see, what is the thinking, and what remembers everything.
I like that.
We can break down almost every modern application into these 3 essential components: the front end, the back end, and the database.
Okay, let's start with the most visible part, the front end.
Okay.
If you stick with our car analogy, this is the dashboard, the steering wheel, the windshield.
It's the entirety of the user experience. The front end is everything the user directly interacts with. It's the visual interface, the specific buttons you click, the fields you type into.
All the stuff on my screen.
All the stuff on your screen. The text you read, the screens you swipe through. It runs locally on your device, so your web browser or the app on your smartphone.
And what's its job?
Its job is really twofold. First, to render information clearly for you, the user. And second, to collect your input, a click, a search query, a login request, and then transmit that request to the hidden components.
Okay, so the front end collects the input, it sends the order. That order has to go somewhere for processing. That must be the back end.
That is the back end. The back end is the engine and the brain. It's the hidden logic, the server-side component. It's what handles all the heavy, complex lifting.
Like what, specifically?
Like processing requests from the front end, performing calculations, executing business rules, and managing critical elements like security and authentication.
So when I log into my bank...
When you log in, the front end collects your username and password, sure. But the back end is the component that actually runs the complex logic to check those credentials against the records, verify your permissions, and then grant or deny access. It is the security gatekeeper and the computational heart of the whole system.
Got it. And if the back end is the brain, we need memory. That's the third component, the database.
The database is the persistent memory of the system. It's where all the data, all the information that needs to survive after a user closes the application is stored, managed, and retrieved efficiently.
So this is more than just short-term memory.
Way more. Think of it as the ultimate library catalog and storage vault. User profiles, transaction histories, inventory counts, every article ever published, every message you've ever sent. All of that lives in a database.
And the back end is constantly talking to it.
Constantly. The backend logic interacts with the database to retrieve information, update records, or create new data, and then it sends the relevant results back to the front end for you to see.
Okay, so what's crucial here, and this is something non-engineers often miss, is that modern architecture mandates that these three components are separate modular parts. They're often built by different teams using totally different programming languages.
And that modularity is the secret sauce. It's the secret sauce for rapid development and for scalability. If you need to refresh the look and feel of the app, that's a front-end update, you don't necessarily have to touch the complex calculation logic in the backend.
And vice versa.
Exactly. And if you need to optimize how data is stored or retrieved, a database update, the front end and back end can keep running as long as they follow the communication rules, which we'll discuss in the next section.
Right.
This separation is absolutely key to efficiency and scalability, which naturally leads us to the crucial question: where does all this complicated machinery actually reside?
Okay, so we understand the components, front end, back end, database,
Mhm.
but they had to physically exist somewhere. For decades, they resided in company server rooms right on the premises.
Yep, in a closet down the hall.
Exactly. But now we talk constantly about the cloud, and we really need to tackle this term because for the average person, it still sounds like something, I don't know, intangible, magical.
Ethereal, yeah.
What is the cloud in practical, non-magical terms?
We need to dispel that myth entirely. The best practical definition for our listener is this: the cloud is just someone else's massive, globally distributed, highly efficient computer.
Okay, say more.
More accurately, it's a vast interconnected network of specialized, standardized data centers. And they're managed by global providers like Amazon, Microsoft, or Google.
So they handle all the physical stuff.
They take on the enormous burden of handling the physical hardware, the network infrastructure, the power, the cooling, all of it. And this allows businesses to just rent computing resources, servers, storage, specialized databases on demand instantaneously.
So the fundamental difference isn't that the data is floating in the air, but that the computing power is. It's virtualized and it's outsourced.
Exactly. We contrast this with traditional infrastructure, or what we call local systems. If an application runs locally, the company has to buy, manage, power, cool, and maintain all the physical server hardware in their own office or some dedicated facility.
Right.
With cloud systems, you're just accessing a shared pool of virtual resources. The shift to the cloud is less about technology, really, and more about financial strategy. It's moving from these large, unpredictable capital expenditures, CapEx on hardware,
Buying a bunch of servers.
to flexible, usage-based operational expenditures, OpEx on rented resources.
And why is that transition so vital? I mean, why are virtually all new large-scale applications now built on the cloud instead of relying on local systems?
It really boils down entirely to two critical, non-negotiable concepts in the modern digital economy. And those are scalability and availability. Local systems they cannot compete with the dynamic demands of a global user base.
Okay, let's start with scalability because this is often misunderstood. I used to think scalability just meant buying one really, really big, powerful computer.
And that's a type of scaling. We call that vertical scaling, buying one larger, more expensive server. But the cloud's true power, its game-changing ability, lies in horizontal scaling.
Okay.
Scalability is the system's capacity to handle a sudden, massive influx of users or transaction traffic without slowing down or crashing. Think about a major global product launch, or let's use the classic example from our sources, a Black Friday sale.
A Black Friday spike in e-commerce traffic is a great analogy. It's the ultimate stress test.
It is. So if you relied on local servers, you might have invested in enough physical hardware to handle your average daily load of, say, 10,000 concurrent users.
Like your normal Tuesday.
Your normal Tuesday. But on Black Friday, when 500,000 users show up in the span of an hour, your system would instantly become overwhelmed.
And crash.
It would result in massive lag or complete failure, leading to huge lost revenue and a lot of customer frustration.
But the cloud solves this by being elastic.
Precisely. In the cloud, the infrastructure allows you to automatically and instantly spin up dozens or even hundreds of smaller, identical back-end servers when that demand spikes. That's horizontal scaling.
So you're adding more servers, not a bigger server.
Exactly. And then when the traffic subsides late Sunday night, those additional servers automatically shut down and you stop paying for them. This elasticity means the system can manage massive peaks in demand without you over-investing in physical hardware that just sits idle 90% of the year.
That dynamic, usage-based capacity is the first pillar. So the second is availability. This is about keeping the lights on everywhere all the time.
Availability ensures that the system is always running and accessible to users globally. 24 hours a day, 7 days a week, 365 days a year. If your application is crucial, say global banking or hospital records, any downtime is just catastrophic.
Right.
If you run a local server room, a simple localized event, a power outage, a flood, or, as we joked earlier, a janitor tripping over a power cord, that can take your entire operation offline for hours, maybe days.
That lack of resilience is a terrifying thought for any global business.
It is. Cloud systems are built with multi-layered redundancy. Your data and your computational processes are often replicated across multiple physical data centers in different geographical regions, sometimes across continents.
So if one goes down,
If a major weather event takes out an entire server farm in Virginia, the application automatically and seamlessly fails over to the identical redundant resources running in, say, Ireland or Japan, and the user experiences no downtime at all.
wow.
This high availability translates directly to customer trust and increasingly to regulatory compliance.
Availability also ties into speed, right? Specifically a concept called latency. Can you clarify latency for our listeners?
Sure. Latency is the delay between a user making a request, like clicking a link, and the system starting to process and respond to that request. It's the travel time for data. So in the context of global cloud architecture, if a user in Australia has to send the request all the way to a single server in London and wait for the response to come all the way back, the latency will be high, the experience will be frustratingly slow.
But the cloud helps with this.
It does. Cloud providers mitigate this by allowing you to host your resources closer to your users. You can distribute the back-end logic geographically, so the user in Australia talks to a server in Sydney. Low latency is just a non-negotiable feature for any modern interactive application.
Okay, so now that we've established the cloud as this elastic, highly available environment, let's revisit the backend and database components within this specialized context. And then let's introduce the connective tissue that makes all this modularity possible, APIs.
Okay, so let's look at servers again. In the cloud, these are highly virtualized computational workhorses. They're interchangeable and they're disposable.
Disposable, what do you mean?
Meaning if one fails, it's instantly and automatically replaced by an identical resource. There's no panic, no one running to fix it. This is what enables that crucial horizontal scaling we just discussed.
Got it. And what about databases? I mean, how do they handle the millions of queries per second required by a global app? That seems like an impossible task for one machine.
It is impossible for one machine. Cloud databases are specialized, managed services that are optimized for immense scale and built-in redundancy. To handle millions of concurrent users, cloud databases often employ a technique called sharding.
Sharding. Okay, what's that?
To put it simply, imagine your database is a massive library. If it gets too large for one building, you split the catalog and the physical books across multiple smaller branch libraries.
Okay, that makes sense.
Sharding is just splitting the data across multiple machines, or shards, so that no single machine has to handle the entire load. This ensures the system can process millions of queries per second while retaining data integrity and availability, even if one of the physical servers fails.
That makes the sheer scale of modern data handling seem, well, at least comprehensible.
Right.
This brings us to the most critical connector in modern architecture, APIs, application programming interfaces. You said this is the lingua franca of the digital world, and for our listeners, we absolutely must demystify this.
This is the concept that ties everything together. Think of the API as the standardized way that different pieces of software or different teams building different services agree to talk to each other. I love the analogy of the waiter in a restaurant.
Okay, let's walk through that.
Okay, so your front end, your phone app, is the customer sitting at the table. You want to order something, which is data. The back end, the kitchen, has the ability to fulfill that order, but you can't just yell at the cooks directly. It would be chaos.
No, you can't.
The API is the waiter. The waiter knows exactly what the kitchen can make, what format the order needs to be in, and how to deliver the final product back to your table. The waiter is the standardized interface.
So when my front end needs a piece of information, say my last 5 stock trades, it doesn't just barge into the back-end server and start rifling through the data.
Absolutely not.
It sends a standardized request via the API saying, hello, here is user ID 123. I request the last 5 transactions in this specific JSON format.
Precisely. The API defines the contract. It's a set of rules. It ensures that the request is formatted correctly, that it's authenticated, and that it's delivered to the correct part of the backend.
And then the waiter brings the food back.
The backend uses that ID to query the database, gets the data, and then the API structures that data perfectly before sending it back to the front end. This standardized communication layer is essential for both modularity and security.
And what happens without it?
Without APIs, every time one component changed, say, the backend upgraded its software, all the other components that talk to it would break. APIs ensure stability and allow different parts of the system to innovate independently. They are, in fact, the key mechanism that allows us to integrate sophisticated intelligence into these systems.
Okay, the moment we mention AI, people's minds go to sentient robots or something entirely separate from the systems we've just discussed.
Right, they think of Skynet.
Exactly. But our sources emphasize a really crucial point. AI is not magic. It is a highly specialized, intelligent component that relies entirely on the existing digital architecture we've just laid out.
That perspective shift is so important. AI models, whether we're talking about a large language model, an LLM, a recommendation engine, or a predictive algorithm, they are sophisticated pieces of software running unbelievably complex mathematics.
Yeah.
And just like any other piece of software, they run on the servers we discussed, they use the data stored in databases, and they communicate with the main application architecture via APIs. It's just another, albeit more complex, workload.
So AI doesn't exist outside of the backend or the cloud. It's just another service running on that scalable infrastructure we established. If my app uses AI, it's just making another, more advanced API call to an intelligent server.
Exactly that. When your application needs an intelligent capability, say, summarizing thousands of customer reviews, the backend doesn't magically develop that capability. It's not sentient.
Right.
Instead, it directs the request to a dedicated AI service, which itself is running on specialized high-performance cloud servers, servers that are optimized specifically for those intense computational tasks. The AI is simply another highly sophisticated layer of the back-end architecture, accessed via that same standardized API contract.
Okay, let's trace the mechanics of this connection. Let's detail the input and output mechanisms for AI within an application connecting all three of our pillars.
Okay, we can trace a clear and critical data path, starting with data input. AI models rely heavily on data from databases in two distinct phases. Phase one is training.
Building the model.
Right. Building the model requires petabytes of general data. This is where the LLM gets its general knowledge of language and the world.
And phase two.
Phase two is real-time inference. This is when an application is actually using the model. At that point, it needs current, factual data to give a useful answer.
Can you give an example of the difference between those two?
Certainly. Let's say you're using a commercial chatbot for a retail company. The general LLM knows how language works. That's from the training data. But if you, the user, asks, what is the warranty policy on product X?
The general model has no idea.
It has no idea. So the AI component must pull the current, accurate product specifications and policies from the company's internal, frequently updated knowledge database. The backend uses the API to ask the AI the question, but the AI uses the internal database to ground its answer in fact. This is what prevents the AI from hallucinating or just making up company facts.
So the database feeds the intelligence with fresh, relevant information.
Yeah.
That makes sense. And then how does that intelligent result get back to me, the user?
That's the application output phase. Once the AI model generates a result, a prediction, a personalized summary, a decision, that result has to be delivered back to the main application efficiently.
And I'm guessing that's another API call.
Almost universally, yes. It's handled via a standardized API call. The main backend receives the AI's output, packages it up as a coherent piece of information, and then sends it off to the front end to display to the user.
So the whole exchange involves multiple specialized servers and database queries. But from my perspective on the front end, it just looks seamless.
It's designed to be seamless. That's the goal. The user only sees the final result.
This structured architectural chain really explains how these complex, intelligent processes can be triggered by just a simple user interaction. Let's make this even more tangible. We found 3 great real-world examples of AI integration in the sources.
Let's start with the obvious one, chatbots.
Okay.
So a user types a complex question into the interface on the front end. That input travels to the back end. The back end then immediately uses an API call to send that question to the large language model, the LLM, that's the AI component.
Right.
That LLM needs context, so it queries the company's specific knowledge database. The synthesized factual answer is then routed back via API to the backend, and finally displayed on the front end for the user to read. It's a perfect illustration of all four parts working in harmony.
That's a great example.
Mhm.
What about recommendations? Like suggested videos on a streaming service or products on an e-commerce site.
Mhm.
This seems like it's entirely driven by data.
It is fundamentally driven by data extracted from the database. The AI component analyzes your user history, what you've watched, what you've clicked, what you've
And
purchased.
not just me, right?
No, and what thousands or millions of users like you have done. All of this history is stored persistently. The AI component calculates these incredibly complex patterns and predicts what content or product you are most likely to engage with next.
And that prediction is the output.
That prediction is the output, which is then fed back via the API to the front end to dynamically curate your personalized homepage. This integration directly drives the vast majority of business value for these platforms. It's a huge deal.
It really is. Okay, and finally, the efficiency play. Automation. This is less about customer interaction and more about, what? Optimizing the engine itself, running behind the scenes.
Exactly. Automation uses AI to take over routine, high-volume, repetitive tasks that are happening within the back-end processes.
Give me an example.
Think about automatically sorting thousands of customer support tickets into the right departments, or dynamically flagging suspicious financial transactions based on learned patterns, or even summarizing vast quantities of daily internal reports for executives.
So it's an internal tool.
It is. This AI component works silently on the servers, processing data from the databases and executing tasks based on predefined or learned criteria. It quietly supports the entire digital structure, and crucially, it frees up human resources to focus on complex, novel problem solving, which is something we're about to get into.
Okay, so we've broken down the entire architecture. We've got the modular software, the powerful distributed cloud, and the integrated AI component. Now, what does knowing all this imply for the people who have to build, maintain, and utilize these systems?
Right.
Our sources highlight that the necessary skill sets are undergoing this massive structural transition.
The central transition, the big takeaway, is moving away from valuing rote knowledge, the ability to memorize facts or execute basic repeatable steps, and moving towards valuing systemic understanding.
And why is that shift happening now?
It's happening because AI tools are already incredibly adept at handling routine, memory-based, and repetitive commands. If a machine can look up a fact or execute a standard procedure instantly and perfectly, the human value shifts entirely to areas where machines still struggle profoundly.
Which means the focus has to shift entirely toward problem solving.
Absolutely. The capacity to troubleshoot novel problems, to diagnose failures across these integrated systems, and to adapt to entirely new, unseen technologies, that is exponentially more valuable than simply memorizing specific commands or syntaxes related to one version of one software program.
Because if a system fails, it's rarely a simple fix.
It's rarely because someone forgot a single command. It's usually because the interaction between the front end, the API, and the sharded database went awry in some unexpected way. The person diagnosing that failure needs to grasp the entire system, not just their little silo.
And this feeds directly into the second crucial skill, which is understanding systems. It's the difference between knowing how to drive a car and knowing how to design a hybrid engine.
That's a perfect analogy. The future workforce needs to grasp the entire interconnected architecture, front-end, back-end, cloud, AI, rather than just mastering isolated tools. If you only know how to code one specific language for the front end, you are a specialist with limited utility when the whole complex machine breaks down.
And that lack of a holistic view is where bottlenecks and big mistakes happen, isn't it? When the back-end engineer assumes the database team structured the data one way, but they didn't.
Exactly. Understanding systems means anticipating those communication bottlenecks and understanding the trade-offs. It means realizing that adding a cool new feature might be easy on the front end, but it might break the scalability limits of the database. This holistic view is becoming mandatory for leadership and high-level decision-making in any digital enterprise.
So let's delve into the specific foundational knowledge bases that the sources identify as gaining immediate importance. And this isn't just for tech people, right? It's for professionals in any industry.
Any industry. We need to look at three key disciplines that sort of transcend specific platforms or software programs. First one, learning Python.
Why Python?
Its relevance is just skyrocketing because it's this incredibly versatile language that is foundational to modern data science, machine learning, and AI development. unlike some older, more rigid languages that require massive amounts of structure.
Right.
Python's flexibility and readability make it the language of analysis and transformation. It's become the gateway skill for anyone working with sophisticated data processes or communicating with AI systems.
So it seems like Python is replacing older languages in these spaces because it's just easier to prototype and integrate new intelligent components quickly.
That's a good way to put it. It's the standard bridge language for moving between data analysis, engineering, and the machine learning models themselves.
Okay, what about data thinking? This sounds a little vague, but I suspect it's incredibly concrete in practice.
It is. Data thinking is the ability to conceptualize, manage, and derive actionable insights from the large data sets stored in those vast cloud databases. And this is crucial for every role, not just engineers.
So a marketing professional, for instance.
Exactly. A marketing professional with data thinking skills doesn't just ask, did our campaign work? They ask, what's the correlation between the demographic data in our database, the click-through rates from the back end, and the sales conversions stored in the database?
They know how to ask the right questions.
They know how to structure the right questions, how to identify biases in the data collection, and how to critically evaluate the integrity of the information they're looking at.
It's the ability to translate those raw numbers into strategic action, which is what gives businesses a real competitive edge.
Precisely. Data is the currency of the digital age, and critical thinking about data, how it's structured, how it's analyzed, is essential for almost every modern role.
And finally, we circle right back to the start of the software lifecycle. Business processes. Why is having commercial acumen now considered a core technical skill?
Because technology is never an end in itself. It's an expensive tool that is used to achieve commercial goals. The most valuable professionals are the ones who understand the core commercial goals that drove that initial idea to software lifecycle.
So they connect the code back to the balance sheet.
They do. They ensure that the technical work aligns with organizational needs. They optimize resources and deliver features that genuinely provide business value rather than just delivering technically interesting but commercially useless projects. Technical knowledge combined with commercial acumen is the highest leverage skill in today's economy.
And this brings us to the ultimate critical takeaway from the sources, really for educators, students, and institutional leaders, the necessary educational pivot.
This is the definitive imperative that was summarized in the source material. Education must fundamentally shift its focus from teaching students how to use tools to teaching them how systems think.
What's the difference?
If we focus on tools, teaching the specific menu structure of one piece of popular software, that knowledge has an expiration date of maybe 5 years. The software changes, the interface moves, the underlying system is refactored, and your knowledge is obsolete.
But if we teach them how systems think, we're teaching the underlying logic, the principles that remain true regardless of the interface.
Exactly. We teach them relational logic, data architecture, networking protocols, problem-solving methodologies based on the front-end, back-end database principles. We teach them the concepts of modularity, the trade-offs of scaling horizontally, and the fundamental role of the API contract.
So you're building adaptability.
You're ensuring adaptability. So when a new technology like AI emerges, a student who understands systems doesn't feel overwhelmed. They simply ask, okay, where does this new intelligent component plug into the existing backend structure, and how does it access the data? That persistent knowledge is what ensures they remain relevant even as technology evolves rapidly around them.
What an extensive, detailed deep dive into the architecture that really powers our modern world. Let's quickly recap the 3 major insights we extracted from the source material today, providing you with that comprehensive shortcut we promised at the start.
Okay. First, we established the modularity of software, that necessary separation of concerns between the visual front end, the logical processing back end, and the persistent sharded database. This structure is what allows for independent updates and massive scale.
Second, we demystified distributed infrastructure. We came to understand the cloud not as a metaphor, but as massive, elastic data centers that guarantee high availability and instantaneous scalability through horizontal scaling.
And we learned it's all connected by those crucial standardized communication channels called APIs.
And third, we contextualized the functional role of AI, recognizing it not as magic, but as a sophisticated integrated software component that runs on the existing infrastructure, leveraging the database for contextual data input and the API for application output.
It's a powerful engine, but it requires that existing, robust digital architecture to function reliably.
And let's reiterate the relevance for you, the listener. Regardless of your current profession, this systemic knowledge provides the context you need to make informed decisions about technology investment, adoption, and education. You can now engage critically with technology, understanding its limitations, its costs, and its vast underlying potential. You have the blueprint.
And as we close, let's look toward that necessary shift in education we just talked about, moving toward teaching how systems think rather than how to use tools. This idea raises a fascinating and I think provocative question for you to mull over in the coming weeks. If the goal is no longer just rote memorization or mastery of specific technical commands, how exactly do educators and employers measure success in teaching systemic thinking and complex, non-repeatable problem-solving abilities? Especially when you consider the limits of our current traditional standardized testing.
That transition from measuring what you know to measuring how you think.
Yeah.
That really feels like the key challenge of the next decade. Finding those metrics for conceptual mastery, not just factual recall. This has been a crucial, foundational exploration of the digital landscape.
And we'll continue exploring these massive topics soon. This structured approach to understanding the technological landscape is just the beginning.
Thank you for joining us for this deep dive into digital architecture. We hope you feel significantly more informed and hopefully less overwhelmed by the complexity of the systems you rely on every single day.
Until next time, keep digging into the sources yourself.
And keep thinking about the systems.